Hello everyone, this is our work, Inverse Reinforcement Learning for Team Sports, Value Actions and Players. This work lies in the research field of sports analytics. Sports analytics provides professional methods for analyzing sports data to facilitate decision-making before and during sports events. In this work, we focus on evaluating players' performance, also known as player evaluation. We use NHL ice hockey data to design our model and evaluate. Our method can be easily adapted to similar low-scoring sports. So how to evaluate players? Most approaches use the total value of players' actions to rank players. This reduces players' evaluation to action evaluation. State-of-the-art methods use reinforcement learning to learn an action value Q function. For example, score and impact use Markov game model to model game dynamics and define advantage value as action impact. The goal impact matrix use deep reinforcement learning to learn Q function and define the difference between two consecutive Q values as action impact. We noticed that in previous reinforcement learning models, they all use sparse reward signal. In low-scoring sports like ice hockey and soccer, if you use sparse reward, explicit values are only attached to real goal events. For example, their action values will emphasize on goals and related actions, such as shots and assists, and their player ranking will bias towards offensive players. For example, we rank the top 50 players for NHL 2018-19 season. The score and impact are all offensive players, and the GIM only contains one defenseman. So in this work, we use inverse reinforcement learning to learn reward for game states. First, we build a Markov game model for ice hockey. The Markov game follows the score and impact work. In the game, we have two agents, home team and away team, and we choose defining features as the state. The features including manpower, which has value even strength, short-handed power play, goal difference, which is the difference between home and away goals. Period ranges from 1 to 3. We do not consider overtime play. And team identity means the current team is home team or away team. And the location. We divide the location into 6 ranges, which is shown in this picture. The hockey rink is divided by the orange line and 2 blue lines. The 2 blue lines are the boundary of the neutral zone. The transition function represents the probability of landing at next state given current state and action. This is calculated using the observed frequency from our data. Here comes to our approach. First, because we use a play-by-play data, which only contains information of players who control the puck, so we cannot really do multi-agent learning. Here we leverage the single-agent inverse reinforcement learning for multi-agent Markov game. Second, because the game is a competition, goal is such real events in our dataset. Directly applying single-agent algorithm fails to learn the importance of goals, so we combine knowledge between observed goals and unobserved rewards. The table below shows an example. We got the sequential data of state and action, and we also know the observed goals. We want to recover the unobserved reward and combine them together to learn an aggregated reward function, then to calculate the value function. For the first approach, we use an alternating learning method. That is, in the Markov game, we get 2 agents, A and B. We first treat B as A's environment and learn reward for A using single-agent algorithm. Then we repeat the procedure with roles of teams A and B reversed. Why we can do this alternating learning? Because we assume 2 policies for agent A and B estimated directly from the data satisfy Nash equilibrium. The Nash equilibrium means each agent chooses a strategy and no player can increase its own expected payoff by changing its strategy, while the other agents keep theirs unchanged. Our assumption is reasonable because each team optimizes against the observed policies of another team. In sports, teams have direct access only to the observed behavior of other teams, and when an opponent's observed behavior falls short of their optimal strategies, successful teams take advantage of it. Based on this assumption, we can transform multi-agent model to single-agent model. The intuition here is if we treat B as A's environment, we can transform the markup game to a markup decision process. And the value function for agent A in the markup game and MDP is identical. For the inverse reinforcement learning algorithm, we use a maximum entropy one. Here are some key aspects. The reward is a linear function of state features. The reward for a trajectory is the sum rewards of visited states. Assuming agents acting on the maximum entropy policy, the likelihood of a trajectory is proportional to exponential reward. The aim is to maximize the likelihood of trajectories given reward, which is parametered by theta. Then we calculate the gradient of likelihood for theta and update the function. For the second approach to combine the observed goals and learned rewards, here we choose a kernel function k to measure the similarity between them. Then the final learning procedure is to maximize the regularized likelihood function. This is motivated by the maximum mean discrepancy framework for transfer learning, and the Gaussian kernel is usually chosen. We first show the learning details and the performance. Recall that in maximum entropy inverse reinforcement learning, we define a linear function for the reward. Then we define a theta 0 to match the goal's reward and initialize the theta with theta 0. The picture below shows the gradient during training for inverse reinforcement learning with and without domain knowledge. If you see the orange line in the figure, the domain knowledge leads to much more stable and faster convergence. Second, we show that our learned reward solves the sparsity problem. Here we calculate the standard derivation of the recovered reward and calculated Q values. We compare the reward with the rule reward function, which are goals, and compare the Q values with the Q provided by goal impact matrix. Though both results show that the values recovered by our method is much denser. We further evaluate our model in a downstream application player ranking. The picture shows the system flow. Starting from the dataset, we build a markup game model. Then we use alternating learning to learn reward for two agents. And we solve MDPs to calculate the value and Q function. Then we calculate the action impact, and finally rank players by their total action values. Here we show the top 10 offensive and defensive players. These are all very famous players that you can find from the NHL website. And our ranking can be used to identify promising players. For example, Murray just started his career in 2017 and drew a salary much lower than other players, but he is nominated as top 50 defenseman by NHL in 2019-20. And our ranking do not have obvious bias towards player positions. Here we rank all the players together, and the top 50 players contain 32 defensemen. And the player ranking do not have ground truth. Here we calculate the correlation with success measures, such as assists, points, goals, shots. Because these statistics are generally regarded as to measure the ability of players, and we can easily get these statistics from the NHL website. Here we compare our method with several traditional and state-of-the-art methods. And apart from goals and three goal-related items, our method achieves the highest correlation. And for those four items, in most cases, our correlation is the second best. A good player ranking metric should be temporal consistent because for players, their performance is really stable across the season. And if the player ranking metric is temporal consistent, we can use it to predict a player's future performance from the past. Here we calculate the correlation between the first n-round player's value with three important success measures, including assists, points, and goals. And we also calculate the autocorrelation, which is a correlation between the first n-round value with entire season value. For the first three figures, our method always achieves the highest correlation with assists and points. For goals, although our method is not the highest, we can see at the very beginning of the season, our method achieves a much higher correlation compared with others. And for autocorrelation, our method is always the best. So here is a summary. We use an inverse reinforcement learning to infer reward for agent that explains its behavior. The two innovations are our alternating learning procedure reduces multi-agent to single-agent problem, and we transfer knowledge between observed goals and unobserved rewards. We show that we learn a dense reward and Q values, and we provide a promising player ranking. Our ranking do not have obvious bias towards player positions, and we do independent validation through established player metrics. Thanks for your attention.